Today's exercises are on machine arithmetic numerical error. So we'll be talking about how numbers are represented in the computer and how the round-off errors associated with those representations propagate when we do calculations with them. The first number system we'll talk about is the 64-bit floating point system. The way this number system works is that for every interval between consecutive powers of 2, starting from 2 to the minus 1022 up to 2 to the minus 1021, all the way up to 2 to the 1023 up to 2 to the 1024, for all of those intervals, we split them into 2 to the 52 equal width intervals, and we put a tick mark at each of those positions. And those are the numbers that we're going to represent. For this last interval between 0 and 2 to the minus 1022, if we continue this pattern of sort of shrinking down each interval between successive powers of 2, we would stop here halfway between 0 and 2 to the minus 1022. And then there would be a bunch of numbers left of that we couldn't represent. And that turns out to be a problem. So we take this last interval and kind of do something unusual with it and spread it out so that its ticks are equally spaced relative to the ticks in the next interval. And that allows us to reach all the way down to 0. And the way that we associate a particular string of 64 ones and zeros with one of these numbers is that we appropriate the first bit as a sign bit, indicating whether it should be a positive or negative number. So we'll forget about that bit and just think about positive numbers from here on. Then we take the next 11 bits and we interpret that string of bits as telling us which two powers of 2 we're between. So if the next 11 bits form the number 1, interpreted as a binary integer, then we'll be in this first interval here. If it's 2, then we'll be in the second interval, and so on up to this last interval between 2 to the 1023 and 2 to the 1024. Then, once we know which two powers of 2 we're between, we look at the last 52 bits and we count up that many ticks. So for example, if the exponent is 1, so we're between these two powers of 2, and the mantissa is 3, then we count up 3 tick marks, and we would be at this third tick mark here. So for example, if you look at 1/2 to the 1022, so that's this number, and you add 6 tick marks, so 6 tick widths. So a tick width in the subnormal range, so where these blue numbers are, as well as in this first normal range, is 1/2 to the 1074. And the reason for that is the full width of this interval is 1/2 to the 1022, and then we're dividing it in 2 to the 52 equal pieces. So if we just divide 2 to the minus 1022 by 2 to the 52, we get 2 to the minus 1074. So if we move over 6 tick spacings from this first left endpoint of one of our intervals between successive powers of 2, and we check out what the string of bits looks like, we get a 0 sign bit indicating that it's a positive number, and then the exponent bits are telling us that we're in this first interval here. And then all the remaining bits are telling us which tick we're on, and we're on the 6th one. So if you interpret 110 as a binary number, then you get 0 ones, 1 2, and 1 4. That adds up to 6. And if we change this number, let's say to 7, then the mantissa changes, scooting us over by 1 tick, but the exponent stays the same. If we wanted to increase to this range, we would start with the left endpoint of that range, and we could move over by, so the tick spacing is going to be 0.5 to the 1073 now because it's gotten wider in this interval. And if we move over, let's say, 14 spacings, then now we're in position 2 with regard to the exponent, and then our mantissa is 14. So that's 0 ones plus 1 2 plus 1 4 plus 1 8. That adds up to 14. So that's how the representation works. So let's jump into this first problem. So if x minus y is 0 in the float 64 system, then that actually implies that x is equal to y. In other words, we can distinguish distinct numbers by subtracting. And that's a valuable property for a number system to have, subtracting to give 0 if and only if the numbers are the same. And we need the subnormal numbers in order to do that. So we'll do the second part first. Imagine if we take all these blue numbers and scrunch them up by a factor of 2 towards the right edge of this interval, 2 to the minus 1022. We would have this huge gap here to the left. So we can make that observation right away without the subnormals. The difference between the two smallest positive numbers. So it would actually be half of what this tick width is, because we would be shrinking these things up by a factor of 2 towards the right endpoint of this interval. So it'd actually be 2 to the minus 1075. But anyway, that would be way, way, way too small to represent with any other positive number in the system. So the smallest positive number would be 2 to the minus 1023 in that case, because here we have 2 to the minus 1022, and we'd be halving that number. So that difference would have to be rounded to 0. However, with the subnormal numbers, everything is fine because all of the smallest possible difference between two numbers is 2 to the minus 1074, and we can represent that number. It's this very first tick here. And for every other pair of numbers, the difference is going to be larger than that. So we're not going to have to round it to 0. We can always at least represent it with 2 to the minus 1074, or maybe something bigger. So with the subnormal numbers, the smallest possible difference is 2 to the minus 1074, and that number is representable. And actually, something a bit stronger is true. All of these differences between consecutive numbers are not only something that you would not have to round to 0, they're actually exactly representable, because all of the differences between consecutive numbers are going to be powers of 2, at least in the normal range, and they're going to be powers of 2 that we can comfortably represent in the system. In this range, the numbers are essentially just integers. They start from 0 and they count over by integer multiples of the tick spacing here. And so subtracting numbers in this range also gives numbers that are representable in this range. Okay, let's look at problem 2. Which of these numbers are representable exactly as a float 64? So 2 to the 1024 won't be, because we see in the picture up here the largest finite representable value is 1 tick spacing to the left of that. So this number is not representable. 4/3, we might have to think about that one a bit. So it's definitely going to be well within the range. It's going to be off here around 1, somewhere in between these two extremes. So we have to come up with some other reason why 4/3 might or might not be representable. And the key observation is that all of these numbers that we're starting from in the left edge of these binary intervals are powers of 2. We're always adding an integer multiple of some other power of 2. And that means that we're always going to get numbers with powers of 2 in the denominator. Because when you find a common denominator between a power of 2 and an integer multiple of another power of 2, then it's definitely going to be a power of 2. So that means 4/3 is not representable. Minus 2 to the minus 1074, so that's going to be 1 tick to the left of 0. And the negative representable numbers are just the negations of all these positive ones. So that one is going to be representable. So that one's fine. 3/8 is also going to be representable because its denominator is a relatively small power of 2. So we can just go to the inverse power of 2, that's to the left of this one, and then count up an appropriate number of tick marks. And there's no way we're going to skip some multiple of 1/8 in between. And maybe we'll look at that a bit closer in a minute. 0 is representable because you can just use all zeros, and you start with the left edge of this subnormal interval, which is at 0, and you add 0 tick marks, and you're going to end up at 0. 1.5 is also representable. We can start at 1 to let our exponent part tell us that we should be between 1 and 2, and then we should add 2 to the 51 tick spacing starting from 1, and that'll take us halfway exactly to 2. 0.8 is not representable for the same reason as 4/3. It has a denominator that is not a power of 2 when it's simplified. So let's take a look at some of these bit strings. So if we check out 4/3, then what we'll see is that in the mantissa, we're using alternating ones and zeros all the way out as far as we can to try to approximate that 1/3 value. And the exponent here is telling us we're between 1 and 2. If we look at something like 1.5, which we decided should be representable, then what you're going to see is that the exponent part is telling you you're between 1 and 2, and then the mantissa is telling you, see there's a 1 at the beginning here. The mantissa is telling you add 2 to the 51 tick spacings to get halfway to 2. 3/8 is going to be a similar idea. So if we look from 13 to the end to see the mantissa, then it's telling us to add, actually in this case 2 to the 51 as well, tick spacings, because you're starting at a quarter. That's the power of 2 immediately to the left of 3/8, and you're going halfway to a half. So this is very similar to 1.5. And then a bit string of all zeros, and gives you the 0 number, and then 0.8 is going to be similar to 4/3. There's some alternating zeros and ones out here as far as you can see in the mantissa, because it's trying to approximate that 4/5 value. In this exercise, we learn about the next float and pre-float functions in Julia, which essentially allow you to count up or down 1 tick in the float 64 system. So for example, the float just above 15 and 15, when we subtract them, and we know this number is going to be exactly representable because it's consecutive numbers in the system, we get a number that's really small. So in other words, we can represent 15 and 15 plus a very small number. And specifically, how small is this number? Well, 15 is between 8 and 16. The tick spacing starts at 2 to the minus 52 between 1 and 2, and then we double it 3 times, going from that interval to the interval from 8 to 16. So the gap between successive representable numbers between 8 and 16 should be 2 to the minus 49. And if we calculate the log base 2 of this value, then we get 49. As we've already seen, the next float above 0 is 2 to the minus 1074. So this should be minus 1074, and that's correct. If we do the difference between 1 and the float before it, then we're to the left of the interval from 1 to 2. In other words, we're between a half and 1, and so the tick spacing should be half as large there. So it should be 2 to the minus 53. Oops. And that's correct. So float 64 arithmetic works by performing the arithmetic operation and then rounding to the nearest number. However, you can be exactly halfway between 2 tick marks, and you have to decide which one to go to. And there's a standard rule for this, and we're just going to investigate that rule here rather than just being told what the rule is. So we define epsilon to be 0.5 to the 52. So this is 1 tick spacing in the interval from 1 to 2. Then we can check if we add exactly half a tick spacing, do we come back down to 1 or do we go up to the next tick? And we come back down to 1. So this, if we ask whether this is equal to 1 tick spacing over, it won't be. However, if we add 1.5 tick spacings, so you might speculate at this point maybe it's rounding down when it's exactly halfway in between. But if you move over 1.5 tick spacings, it does not round down. So it actually rounds up. If we go over 2 tick spacings, then that checks out. So this side is exact because we're dealing with numbers that are representable, and this side has to be rounded because we're landing halfway in between numbers that are representable. So what we're seeing here is that we have actually a round to even rule. So we round to the even index tick, whether it's the one to the left or the one to the right. For example, if you go up 7.5 tick marks, you're going to round up to 8 tick marks to the right. And this is true between 1 and 2, but it's true also between any other successive pairs of 2. Whenever you land between 2 tick marks, you figure out which one of them is even indexed, counting within that interval. and you move left or right to whichever one is even. In this problem, we'll think about how the float64 spacing trades off against the very large range of integers that are represented. So if you look back at this picture, you can see that this last interval has a width of 2 to the 1023. So if we subtract 2 to the 1024 minus 2 to the 1023, we get 2 to the 1023. So that's the width here. And we're only splitting that last interval up into 2 to the 52 pieces. So that means each one of these pieces is going to be an enormous number, 2 to the 971. And so we go from representing numbers which are extremely close to each other to representing numbers which are actually very far apart on the upper end of the spectrum. And the question is, where does that tipping point happen? Where do we go from being able to represent fractional numbers to only being able to represent integers to, in the next interval, only being able to represent even numbers, and then from there powers of 4 and so on until we get to these very large powers of 2 all the way at the right end. To answer that question, we can just think about what happens in this picture. Imagine extrapolating it, going from this interval from 1 to 2 to 2 to 4 to 4 to 8, 8 to 16, and so on until these intervals widen out to have a unit width. And so the question is, how many times do we have to multiply 2 to the 52 by 2 in order to get 1? And just looking at the equation, you can see that the correct value is 52. So in the interval from 2 to the 52 to 2 to the 53, we have a width of 1, so we're representing exactly the integers. So we've talked about how numbers are represented and rounded. Now let's transition to talking about how those round-off errors propagate through a calculation. So in the simplest case, we can look at a function from r to r, and we can think about what happens if the input changes from a to some nearby number a plus delta a. The output changes from s of a, whatever it was before, to approximately s of a plus the derivative of s times the change in input. So that's how derivatives are defined, as the quotient of the change in the function to the change in input. And unpacking that, you can say the change in the function is a derivative times the change in input. But if we're interested not in just how the function changes, but how the function changes in relative terms, so if we make a particular relative change to the input, and we want to see what the relative change to the output is, then we get a little bit different formula. It turns out to have the derivative in it, but then there's also these extra two factors. So we divide by s of a, since a really large output results in a smaller relative change in the output. And similarly, we multiply by a in the top, since if the input is very small, then changes in the input are larger in relative terms. So we call this value the condition number. It's like the derivative, except it's measuring relative changes instead of absolute changes. And it basically is the derivative, except we have to multiply by this extra scale factor of the input value divided by the output value. And the condition number has some maybe kind of surprising properties if you're used to thinking of the derivative as measuring how well behaved a function is, in the sense of not being too steep. The condition number is going to give you some different behavior. So for example, the condition number of the function that maps the input to its nth power is actually constant. So the condition number is n. So if n is large, then the condition number is quite large. That means a small relative change in input is getting multiplied by this large number n. But it's not that crazy. Even if a is like 10, you're only multiplying your errors by 10. It's not blowing up to some arbitrarily large number. However, the condition number of the function which just subtracts 1 does blow up, near 1 specifically. And this is a function, if you graph it, it's just a straight line, has a slope of 1, it seems perfectly well behaved, but the subtraction of 1 is actually affecting the condition number in a very serious way. So this is something we'll see quite a bit, and it's something to watch out for. It's called catastrophic cancellation. So the point is that if you're subtracting two very close numbers, then you have to represent those numbers with exceptionally high precision for the difference to be represented very accurately. So let's see a specific example of how that can play out. So if a condition number of a problem is large, then that means that even if you solve the problem perfectly, any small errors in the initial data of the problem lead to a large change in the result. So errors get multiplied by the condition number, relative errors get multiplied by the condition number when you solve the problem. So that means if the condition number is very large, you're just not going to be able to solve it with high precision. So such a problem is called ill-conditioned. And if a problem is well-conditioned, though, it has a modest condition number, then in principle it should be possible to compute the value without losing very much accuracy. So specifically, we look at machine epsilon, which is 2 to the minus 52. So that's the relative precision of the number system. It's 2 to the minus 52 if you're using float 64s. In a different system, it might be smaller or larger if it's a more or less precise number system. But basically, you should expect generally your error encoding the initial data of the problem to be at least machine epsilon, and that gets multiplied by the condition number kappa when you solve the problem. So you should expect to get an error of around kappa times machine epsilon if you solve the problem well. However, you can choose bad algorithms for a problem. You can choose an algorithm that has an ill-conditioned step in it, even if some other algorithm might exist that doesn't have that step in it. And then you're going to be getting relative error that's much larger than it has to be. It's much larger than the condition number of the underlying problem itself. And such an algorithm is said to be unstable. An algorithm that solves the problem with a relative error that's about the condition number times machine epsilon, we call that stable. So again, stability refers to an algorithm and conditioning refers to a problem. So a problem is an abstract mathematical entity, and it has nothing to do with a particular way a computation might be performed. And it's essentially telling you, conditioning is telling you whether the problem is solvable in principle with high precision. And stability has to do with how you go about it. And if you're achieving approximately the theoretically achievable relative error magnification, then the algorithm is stable, and if you're not, then it's unstable. So here's a really common and simple example of this. So if you want to compute the function square root of 1 plus x minus 1, typically the way you do that is add 1, then square root, then subtract 1. That's what the expression tells you to do. And it turns out this is an unstable algorithm for computing this quantity. So we define our function square root of 1 plus x minus 1, and this is actually defining a function and an algorithm for computing the function. We can define a function that's mathematically equivalent by performing rationalizing the numerator operation. We can compare the values you get when we plug in the same number, 10 to the minus 12, into the original function with the unstable algorithm, the new function with the stable algorithm, and we'll also do it with big arithmetic here, which will give us a lot of precision, and we can see which one of these is more accurate. And the first one where it turns 5.000 times 10 to the minus 13, but then the digits start to become something else. The second one gives us far more digits of accuracy here, actually all the way out to 875. You can see in the big number arithmetic, all of those digits printed there are accurate. This algorithm is stable. The reason that this algorithm is unstable is that it has this subtraction operation. So we decided that subtracting 1 from a number that's very close to 1 has a large condition number. So even though the function itself, if we computed its condition number, we would get something that isn't blowing up. And we can see that because we can compute the value of the function with high precision using the second algorithm. This first algorithm does involve one ill-conditioned step, and that's going to cause the accuracy to degrade. Because when you're performing successive operations, if you have an ill-conditioned step and you blow up your error by a lot, the later steps are not going to allow you to recover that. So an algorithm is stable if all of the steps that it performs are well conditioned, and it's going to be unstable if it performs any steps which are ill conditioned. So we have one last problem here for the condition number, and here we're going to be looking at condition number for a vector valued function of vectors. The idea is to just have a worst case mentality here. You want to think, what's the worst situation for a particular input vector x, and the direction in which the error happens to occur. So conceptually, what we want to do here in this worst case thinking is find a vector that gets shrunk down by a lot, so that the relative error measured on the output side is going to be as large as possible. And we should find a direction for the error vector which gets stretched as much as possible, because we're trying to maximize the error. So we're trying to maximize error, minimize the magnitude of the output, so that we're maximizing the relative error. And the singular value decomposition just gives us a totally direct way to do this. So here's an example of a sort of almost singular matrix that has a 1.2 instead of a 1 in this top right corner. And the singular values are quite different. So one is 2.1 and the other one is about 1/10. And that means that you're scaling space out by a factor of 2 in one direction and then scrunching it down by a factor of more than 10 in the orthogonal direction. So if you want to maximize the relative error, you should choose as your starting vector one of these vectors that's getting scrunched down by a big factor. And you want to choose the error in the direction of the biggest singular value so that it gets stretched as much as possible.